Organic chemistry is the study of carbon-containing compounds and their properties. Organic compounds typically contain chains or rings of carbon atoms. It's mostly studied in living systems like biomolecules. So I know in biology you have a whole unit on organic chemistry because it contains a lot of biomolecules. There are a couple of exceptions. So the carbon-containing compounds like carbon oxides, carbon monoxide, carbon dioxide, all of those are not organic. Carbonates are also not organic. So these types of compounds, even though they contain carbon, are considered inorganic. Some vocabulary: hydrocarbons are the compounds composed of carbon and hydrogen. If it's a saturated hydrocarbon, then all the carbons have 4 single bonds. So carbon, having 4 valence electrons, needs 4 more to make the complete octet. So carbon will always have 4 bonds. If they're all single, then they're saturated. Unsaturated means that you could have a multiple bond, so you could have a double bond or a triple bond. A structural isomer just means that you have the same atoms, but they're arranged differently. There are 3 different endings to our organic compounds, and that tells us whether there's a single, double, or triple bond. So alkanes are ane, and they're all single bonds. Alkanes have the double bond, they end in ene, and alkynes, yne, have the triple bond. And you can use the little formulas here to figure out the number of carbon to hydrogens if you wanted to. The number of carbon atoms, the first 4 are kind of special prefixes, and then it just goes into the prefix that you should know from covalent naming. So 1 is meth, 2 is eth, 3 prop, 4 but, 5 pent, hex is 6, 7 is hept, oct, non, and dec. So again, the first 4 are probably new to you, but the rest of them should look like the covalent naming. So, alright, so if we start putting this stuff together, propane, prop means you have 3 carbons, ane means they're all single bonds. So we have 1, 2, 3 carbons. Each carbon has to have 4 bonds, so I know the rest of this would be hydrogens. So this is propane. So it would be C3H8. So for the hydrogen, you can double the carbon and then add 2. 1 pentene. So pent means 5. The ene tells me that there is a double bond. This number tells me that it's on the first carbon. So when I draw my 5 carbons, I know the first one is where the double bond occurs. So again, they all have to have 4 bonds, so I can fill in with my H's. And so we would have the formula C5H10. So to figure out your number of hydrogens, you would just double. Here we have cis-2-butene. So butene again tells me I have the double bond. But means 4. Now this cis part means that the molecule is bent on that double bond, and that the 2 end carbons are going to be bent the same direction, like that. So then I would have my hydrogens down here at the bottom. Now you don't have to write hydrogens, you could just leave it with the carbons because it's understood in organic chemistry that the rest of the bonds would be hydrogen. So what would the formula be? You would have C4, and then because there's a double bond, we would just double our number of carbons. So it'd be C4H8. So you could have cis where they're on the same side. If it was bent to where it was on opposite sides, like that, this would be trans. Okay, instead of having hydrogens attached to the carbons, you could have other things. You could have a side chain, methyl, ethyl, propyl. You could put your halogens, chloro, bromo, ido, fluoro. There's a whole list of side groups that you can have. Anything attached that's not a hydrogen would be a side group. Alright, so we have 2-methyl-3-octene. So the ENE tells me that there's a double bond, and the number 3 tells me that that's where the double bond is located. Oct means 8, so I have 8 carbons. So on the third carbon, 1, 2, 3, I have that double bond. Now you could start counting from this end and go 1, 2, 3 and put the double bond here. It doesn't matter. I have a tendency to go left to right. 2-methyl. So on the second carbon, instead of having a hydrogen, I have a methyl group. So here's my second carbon, and I'm going to attach a methyl group. Methyl meaning 1 carbon, so it's a CH3. It's missing the 4. It's not 4 because it's attached to the carbon, and that would be your 4th bond. 2,3-dimethyl-2-butene. So but means 4. E and E would be double bond. The 2 would be where the double bond occurs, and then on the 2 and the 3 carbon we have a methyl. It's dimethyl because both of those are methyl side groups. When you start naming it from the structure, it becomes a little bit more complicated. You want to find the longest chain of carbons possible, and you want all side groups to be on the lowest numbered carbon. Alright, so we're going to look at some possibilities for this structure. We have 1, 2, 3 carbons, but then it's not chained anymore. So obviously going down would not be the best case because I have all those other carbons. So we're going to continue this way. 1, 2, 3, 4, and then I can turn again. So I could go 5, or I could keep going down. Well, going down is going to give me 2 more carbons as opposed to 1, so we're going to go down here. 5, 6. So the longest chain of carbons that I have is 6. However, I want to make sure that my 2 side groups, my 4 side groups, here's another one, are on the lowest numbered carbons. So we can number it like this in blue and go 1 to 6. Or we could start over here and call this 1, 2, 3, 4, 5, 6. So which one would be the lowest number? Well, we would have, if for blue, we would have 2 side groups coming off of 2, 1 off of the 3, and 1 off of the 4. But if we numbered in red, we would have 1 on 3, 1 on 4, and 2 off of 5. So the blue numbering is the best way to number. Alright, so we have 6 carbon chain, so that's hex. They're all single bonds, so A and E. Then we want to look at our lowest number, we want to put our side groups in alphabetically. So we have chlorine and methyls, so chlorine would come first. So we have a chlorine on the 5 and on the 4. So 5,4, dichloro, because they're both chlorines. And then we have a methyl group on the 2nd carbon and on the 4th carbon. I didn't give myself enough room here. Dimethyl. Hexa or hexane. Instead of chaining, you could put these into cyclic compounds. So we have 1 bromo, 2 methyl cyclohexane. So hex means I have 6 and they're in a chain. In a circle. A and E tells me that they're all single bonds. I have on the 1st carbon a bromine. It doesn't matter which one that you claim to be 1. I like to use the top as 1 and then go clockwise, but it doesn't matter. So that means on the 2nd carbon I have a methyl group. And again, remember, we could fill in to make all the carbons have 4 by using our hydrogens. Down here at the bottom, we have 1-tert-butyl-3-methyl-cyclopentene. So pent means 5 this time. So it looks more like a house. On the first carbon, I have a butyl group. Now this tert just means that it's coming off of a ring, so it's not going to be 4 chained up. It's going to be in this structure. So we have these 4 carbons coming off of the ring. So that's where the butyl comes in. The tert tells me that it's not a straight line of 4 carbons. On the third carbon, so if this is my 1, 2, 3, I have a methyl group. Now there is a shortcut way of showing where the carbons are located. Let me erase this duplicate here. If you have 2 side groups and they occur on carbons that are side by side, you could call that ortho or O. If you have carbons coming off of if you had side groups coming off of carbons with 1 in between, then that's called meta, or M. And then if they're on complete opposite sides, you would call that para, or P. So instead of numbering 1 and 2 for your side groups, you could just say ortho.